Let's take a quick detour on the way to our next topic. This is a thing we're going to need in a couple of weeks, but it's useful to see it now because it does play in a little bit to the next thing I have to talk about, and it's just generally a nice way of cleaning up our code and making our code more modular. So here's an example. This is an adapted lab exercise from a few weeks ago. Suppose that I'm working on this piece of code that includes tons and tons of functions that work with these arrays of 3 doubles. And you can use your imagination. I got bored after 2 functions, but you could imagine I could write a library of 100 different functions that are constantly trading in these arrays of 3 doubles. And obviously the intention, if we're looking at functions called dot product and cross product, is that these arrays v and w are meant to represent vectors. And then down here, I create some vectors, and there's a vector to use for output. I store the cross product of 2 things in a 3rd vector, whatever. Okay, fair enough. So I can obviously do this because you've done basically this as a lab exercise. You just did an assignment that was full of features like this. But what I want to ask about isn't can we pass arrays into functions? Isn't there a hazard if I change my requirements after this code is already written? So for example, what if I ask, hey, could we use long double instead of double here? Could we use float instead of double? Well, sure, but if you have to change the whole library to use float instead of double, you're changing a lot of stuff in the file. You're not necessarily replacing every occurrence of the word double with float. Maybe just the vectors are going to be floats or long doubles, not necessarily things like the return value of this function. It can be really onerous to have to go through a library you've already written and make that change everywhere it needs to occur because it's easy to miss something. Similarly, what if I were to ask, hey, I don't want to worry about vectors of length 3 anymore. I want to rewrite this to work with vectors of length 4 or 7 or something like that, some other fixed length. Well, that would be pretty annoying because everywhere in the file that I've referred to that size would now have to be changed. And that includes things like this result here. It includes things like the size that I give inside of main to my vectors that I create as sample inputs. Okay, so if only there were a better way of doing that. And it's a feature that does exist that I'll show off in a minute, but really, to be honest, it isn't so useful for this example as it is for one of the next things we're going to talk about. But there is this feature in C that allows me to define my own custom types. And what it really is doing is allowing me to rename some existing type, in other words, the type I could give to a variable anyway. It allows me to rename some existing type with a custom name and then use it over and over again. So here I have this function dot product that takes 2 arguments of type vector. And here I have cross product that takes 2 arguments of type vector and then a vector to store the result. And then down in main I create 3 vector objects. And the feature in question is something called a type definition, and we abbreviate that in C as Typedef. That's what I want to talk about quickly before we move on to our next topic. So when you use the Typedef statement in C, you are creating a brand new type. And after you've done that, anything that can see the typedef, anything in the same scope as the typedef, can then use that type. So here I've created a type called vector, and I use that type as the argument type in the dot product function. I use that type in the cross product function, and again in main. So then the question is, okay, so apparently the typedef directive allows us to specify our own types, but how do we use it? And it's actually fairly simple. Basically, if you can declare a variable of whatever type you want, you can create a custom type. So here's the way this works. First, the first task here is I want to define a custom type called vector, which will be an array of 3 double values. Okay, so the name of the type I want is vector with a capital V. So the first step in defining your own type is declare a variable, just an ordinary variable, that has the properties you want and uses the name that you want to use for your type. So I want a type called vector that's an array of 3 doubles. So I'm going to begin by declaring a variable called vector of 3 doubles. Okay, there it is. Once I have a valid variable declaration for the type that I want, I just put the word typedef in front of it. And once I've done that, now instead of declaring a variable, this statement does not at the moment declare a variable. Instead, it declares a brand new type. And just to be clear, when I say typedef, I'm not saying create me a vector. I'm saying create a new type. And no vectors get created unless I declare one in some function down below. So for example, down here in main, I'm declaring a bunch of vectors on line 19. Okay, so this is how we define a type called vector. Now I want to define a 3 by 3 matrix. It'll be called matrix 3 by 3. So I begin by declaring a variable that has the type I want. The type I want here is a 3 by 3 array of doubles. I give the variable the same name as my eventual type will have. So it's a 3 by 3 array of double. Okay, and then I go back to the beginning and I put the word typedef in front of it, and that changes it from a variable declaration to a type declaration. Okay, and then down here finally, let's define a custom type called coefficient, which will be a single float value. Okay, well if I wanted to declare a float called coefficient, I would do it like this. And that means that if I wanted to create a new type, I would just put the word typedef in front of it. And once you've done that, any use of that new type that we've just created behaves exactly as something of the type that you've constructed around it. So vector refers to an array of 3 doubles, which means if I create a vector down here, I can use it just like I would use an array of 3 doubles. So it's got, index 0, index 1, index 2. I could choose to initialize it, as you can see in this example here. I initialize it just like I initialize any other array of 3 doubles. And in fact, if there were a function that took an array of 3 doubles, even if it didn't use this name, you could pass in a vector and it would be considered the same thing. And similarly down here, I have my type coefficient, and I initialize it just like I would initialize some other float. So why is this beneficial? Okay, well, one, it allows me to easily centralize where I define my type. So if I define type vector up here, then I just change. If I decide later I want the vectors to be floats and not doubles, or if I want them to be ints or something, I only have to change it in one place. It's sort of the type analog of why we use functions. But beyond that, it also makes our code a lot more readable. Even if I had never intended to change the element type of the vector or its size, being able to take arguments of type vector as opposed to some generic double array makes it much more obvious to somebody looking at my code what I'm intending to do with that argument. And that helps the code be readable. And it also helps enforce a sort of uniform sense of style when you're writing a large library that has a lot of functions that do similar things. So we'll see coming up that there's a really important reason that we need typedef that we can't quite get to yet. That I think is next week's material. That basically amounts to the types we're going to be working with in a couple of weeks are very complicated. It takes a long time to write them out. So we need the ability to take a type and then give it some easy name. But for now, we should think about it as some optional feature that allows us to create our own custom types with names that allow our code to be more readable.